Okay, hi, my name is Nicole. This is my video walkthrough for the CS2000 TA application. So here I have this induction problem from the lecture notes, which says for us to prove the geometric series formula, which is essentially the summation from I equals 0 to n of x to the power of I equals 1 minus x to the power of n plus 1 over 1 minus x for all n in the set of natural numbers and for all x in the set of real numbers excluding 1. So given that this is an induction problem, I think it's important for us to first understand exactly what we're trying to prove. So we know that we have to prove this statement, essentially this formula, for this range. And so we know that we have to, in this case, induct on the value n, since we're trying to prove that this equation holds for all n in the set of natural numbers. And we can recall that the natural numbers is defined as the set 0, 1, all the way to infinity. So the good thing about induction problems is that we have a very clear structured formula for approaching these problems. We know there's always 4 components to any proof that we write, and those 4 components are the inductive statement, the base case or base cases, the inductive hypothesis, and then finally our inductive step. So to solve this problem, we can go very systematically in a way and just go through each of our 4 steps and see where that takes us. So starting with our inductive statement, the inductive statement is always in the form P of n equals something. So to be more specific about this, the inductive statement is the exact claim that we're trying to prove for each n. So in this case, or in most cases, we can take our inductive statement directly from our problem description. In this case, we have P of n, or maybe colon would be better here, is our geometric series formula. Because again, this is exactly what we're trying to prove for each n. So our first step is very simple. This is just our P of n. And what's important to note here is that we never want to quantify our inductive statement. So don't quantify n. We will define n more specifically later on in the proof. So now going into our base case, or base cases. So our base case, the reason why we have a base case in any induction proof is to essentially define that lower limit for which our inductive statement holds. We want to have essentially a starting point that we know is true that we can start at to prove that each sequential step in our range is going to hold for whatever formula or equation we're trying to prove. So in this case, to figure out what exactly our base case should start at or what our base case should be, we can look at our problem description again, and we know, once again, that we're inducting on n, which can be in this range of the set of natural numbers, and we know that the smallest natural number we have is 0. So in this case, it makes sense that our base case should be n equals 0. So to prove that our base case is true, or that P of n is true for our base case, we just need to show that the left-hand side and the right-hand side of our geometric series formula equal each other when n equals 0. So we can do some simple algebra here. Our left-hand side becomes the summation of I equals 0, in this case n equals 0, so I equals 0 to 0 of x of I, which simply simplifies to x of 0. And we know for any, just from algebra, any number to the 0th power should be 1. Our right-hand side is 1 minus x to the 0 plus 1 over 1 minus x. Simplifying, this becomes 1 minus x over 1 minus x, which becomes 1. So we can see in this case that our left-hand side and right-hand side give us the same value of 1, which means our base case holds. Okay, now moving on to our next step, which is the inductive hypothesis. So for induction problems, the way you write your inductive hypothesis depends on whether or not your induction problem is one of 2 problems, a weak induction problem or a strong induction problem. Weak induction problems only require the truth of one specific value of n to prove for all subsequent values. And strong induction requires that you assume the truth for a certain range of values of n, and in this case is where you would have like multiple base cases, because just the truth of one particular value isn't sufficient for your proof to work. So we can see here that we only have one base case, and based on this geometric series formula, it makes most sense for us to do weak induction in this case. So our inductive hypothesis is to assume P of k holds for some arbitrary k in the set of natural numbers. And the reason why we say an arbitrary k in the set of natural numbers is because, again, going back to our problem description, we want to prove that this geometric series formula is true for all n in the set of natural numbers. So these two like quantifiers are corresponding. Okay, and then lastly, most importantly, we have our inductive step. So in our inductive step, our goal, or what we want to show, is that P of k plus 1 is true. And at some point, we're going to want to apply our inductive hypothesis to help us along this process. So what exactly does it mean to show that P of k plus 1 equals true? Well, this means that, going back to our geometric series formula, this means that we want to essentially show that the summation of I equals 0 to k plus 1 of x to the I equals 1 minus x to the k plus 1 minus 1 over 1 minus x. And again, this is directly taken from this geometric formula. In this case, we're plugging in k plus 1 for n in all the spots that we have n. So right here too. Okay, it might help us a little to simplify this right-hand side a little bit further. So this right-hand side becomes 1 minus x to the k plus 2 over 1 minus x. Okay, not sure why I wrote this here. This should be a plus 1. Cool. Okay, so our goal is to show that this side equals this side. And so what we can do is try and do some algebraic manipulation on this left-hand side to see if we can make it look like this right-hand side somehow. So we also know that in any induction problem, we're going to try and apply our inductive hypothesis at some point. So our inductive hypothesis, again, is that we're assuming that P of k holds. We can express this more mathematically and see if this provides any hints on how to solve this problem. Given that P of k holds, we know that this following statement is true. That's the summation of I equals 0 to k of x to the I equals 1 minus x to the k plus 1 over 1 minus x. So looking at this left-hand side here, considering this is the summation of all k plus 1 terms, we know this is the same thing as summing from I equals 0 to k plus that k plus 1th term. So we can actually break down this summation into the summation of I equals 0 to k xi plus our k plus 1th term, which is simply x to the k plus 1. Okay, now we can see here that this term right here, this I equals 0 to the k, the summation, matches this left-hand side of the inductive hypothesis that we're assuming to be true. So in other words, we can substitute in this expression into here, which then gives us 1 minus x to the k plus 1 over 1 minus x plus x to the k plus 1. Okay, and now we can combine these terms just with some algebra, multiplying this second term here by 1 minus x to get all the denominators the same. We get 1 minus x to k plus 1 plus x to the k plus 1 times 1 minus x over 1 minus x. Now we can combine some terms here. We can also simplify this further. This ends up giving us 1 minus k to the power of 1 minus x to the power of k plus 2 over 1 minus x. Okay, so what we just did essentially is start from our left-hand side. I'm going to switch a different color here. We started from our left-hand side here. We rewrote our left-hand side using this definition summation into this. And we then applied our inductive hypothesis. Just going to make this very clear. We implied our inductive hypothesis to, again, rewrite our left-hand side further. We did some algebraic manipulation, and then we ended up with 1 minus x to the k plus 2 over 1 minus x. Sorry, that's a bad color. This color. And we can see that this is exactly what our right-hand side of this geometric series formula is. So essentially, at this point, we've shown that our left-hand side and our right-hand side are equal for p of k plus 1. Or in this case, that p of k plus 1 holds. And so this is the end of our proof. We've shown that our base case holds, and that after implying our inductive hypothesis, that p of k plus 1 holds. And so by mathematical induction, p of n holds for all n in the set of natural numbers. Okay, that is the proof. Thank you.